So let's start. We have a lot of material today and only an hour. Usually I give this talk with quite a bit more time, so I'm going to try and squeeze as much as I can without overwhelming you guys. My name is Michael Millerud. I'm a program manager in Windows Fundamentals at Microsoft. And I came here to show you some really exciting tools. So just show of hands, how many of you have actually done performance work before? Wow, quite a few. So I'll be faced with a few experts. And how many of you know what XPerf is? Good, good. So I'm hoping that by the end of today, in an hour, actually, you'll get excited just as me about the tools, and you'll be applying them moving forward in your work. Because I was previously a developer, and I switched to PM this tool because I really believe in what it can deliver for the developers. So some of the objectives today for the session that I would like to get out of it is for you to understand that performance is critical, and since you all raised your hand, you know that performance is critical. I'm not going to even bother selling you on it. I'll show you how to do performance analysis on a live production system, and that's probably something most of you have not done before. Most of you have done lab-based or dev machine-based analysis. With this tool, you can actually go and capture data from a real machine, live production, even a server running production environment. I will talk about WPTKit, Performance Analyzer, and XPerf tools, and I'll tell you how they all relate together. And I'll show you how to collect a basic performance trace. We'll actually collect live data here in a demo and do some very basic analysis. Don't expect to come out of this experts. It will take months to actually become very knowledgeable with the tool, but you'll get enough to be able to jumpstart yourself and go and explore more. So here's a brief agenda. We'll go through the motivation. Again, I will not spend too much time motivating you since most of you came here because you care about performance. I was actually looking through the various sessions, and right now there are 2 other sessions on performance. So thank you all for coming here. I think you made the right choice. I'll then do an overview of WPTKit and go through some key concepts you absolutely need to know to do analysis. And then we'll show some case studies of real performance issues from customers. So this will not be some contrived synthetic stuff. This will be from real machines. And we'll conclude. And hopefully we can do this all in 60 minutes. So how do you ensure that performance is good on a machine? Performance is a very broad term, right? Many people think about performance differently. We tend to recommend that you focus on 3 different axes when you think about performance, and that's responsiveness, resource utilization, and good citizenship. So responsiveness is probably the easiest one to convey, because if your machine is unresponsive, if your system, be it a laptop, a mobile device, a server, is not responding to what the user is expecting, the customer will never be satisfied, period. You will lose that customer. Now, that doesn't mean that machine has to be instantaneous. If it takes 5 minutes, 10 minutes to respond to something, that's fine. Set up the expectation, put a dialog box, never hang the UI, basically. The second point is resource utilization. And you have to realize that underlying your software, whatever you're running, there will always be a CPU, disk, memory, network. Power is another resource people don't realize that you're consuming. You're sharing this with other people on the same system. So make sure that you don't use too much of it. Which really brings me to the third point, good citizenship. It takes only one guy, and you'll see this today in case studies, it takes only one guy to completely ruin a great system. So you can spend millions of dollars, you can spend years developing that system. One guy will come in, put a driver, service, application, and it's done. It's basically end of story. So when I talk about resources, I said CPU, disk, right? It's a bit more to that than this. When I talk about CPU, it's processor time that we really care about. How much time am I spending on the processor versus letting it do other things? When I'm talking about memory, it's really physical memory space, virtual address space, just how big my footprint is in memory. Disk is typically disk service time. Disk is a very simple device, right? It's read, write, and flush. But you would not believe just how many ways there are to really mess up when you use disk. And you'll see an example of this today. Again, network is bandwidth, and battery is something people don't realize is an underlying resource for all the other resources you use on the system. So the more work you do, the more battery you consume. Ultimately, one thing I want you to get out of this is that machine constraints are really your resource usage limits. Whatever you have on the machine is all you have to go by. There is nothing else, so you have to work with the machine. So without boring you too much, I'm actually going to go and show you the tools. And this machine has never had XPerf on it before. I brought an MSI. This is an MSI you can get from the Windows 7 SDK. I will not really spend the time downloading it. This is, I believe, x64 version. Yes. So I'm going to install 64-bit tools. And you'll see that it's a pretty small download. It's only 20 meg. So this is very much unlike Visual Studio, where it takes you quite a bit of time to go and install this. And this is something you can put on any machine. In fact, the tools are X-copyable. Once you put this on my machine, you can actually take this, and it's going to be somewhere here in program files. And really all you need to do is copy those files, X-copy them to any machine. It will work. If you want to do capture, you really just need to copy 2 files, this and this, period, and that will work. For analysis, you need quite a few more bits. So what did that do? I now have in my start menu Microsoft Windows Performance Toolkit. That has a bunch of tools. There's GPU View, Performance Analyzer, WPF, Performance Suite. If you've seen WPT, you notice that over time it actually added more and more tools. It's a toolkit, right? I'll only be talking about Performance Analyzer. That's a tool suite of several tools. Those tools, in fact, that's what is Performance Analyzer. Those are the other tools in the toolkit. And I will primarily focus on XPerf. I will not cover much of the other tools that are in this tool suite, just we don't have enough time for this. So XPerf is a tool in the Performance Analyzer tool suite that is part of the Windows Performance Toolkit. So don't get too confused about it. So let me go and capture a trace. I'll go to command prompt. And I'm already running administrator. It is important that you do run administrator. There is no way to capture trace without being admin. You would actually get an error saying you need privileges, access is denied. And that's because ETL files, which is what we're really capturing, contain a lot of PII information, process names, file names, registry names. Everything you access, you will see. So XPerf will actually be in the path now, and I can go and run it. So let me go and do XPerf-profiles. And what this does, it lists me a set of built-in profiles, each of them defining the various things I can capture. It is very important to capture just the right things, and I'll talk more about this later in the talk. But we will use, for starters, just one of those profiles called general profile, because it's the general one. It captures the most data that we usually need. And you'll see that there's 2 different ones. There's in-sequential file and in-buffer. So while I'm capturing, I can talk to this. There are multiple ways of capturing data. You can capture the events into memory, or you can capture them into a file. And which technique you use depends on what it is you're analyzing. If you're analyzing memory, you probably don't want to enlarge your memory footprint. If you're analyzing disk, you probably don't want to log onto disk. Right now, we're actually logging. Believe it or not. Can I make the font bigger? I can make it like this. Or actually, what I will do is I'll just zoom in anytime. So this is what I ran to start capturing. And right now, my machine is capturing. If you look at this machine, is quite powerful. If you look at this machine, it's yeah. I wish I had a dev machine like this. It's not really affecting my machine much. Nothing is really happening. At the same time, I'm capturing right now every single context switch, every single disk I/O event on that system. Now, of course, granted, it's not doing much. I need to actually go and do something. So let's actually go and do something. How about I search PDC? Maybe channel 9. I actually want to play some video. Oh, there you go. Now, those tools actually work equally well even on a small netbook. So some of you have actually received netbooks here, and you can go and use that same tool. It's been used to optimize Windows from the netbooks all the way up to high-end servers, so it scales to 128 way machines and down to a single processor machine. Now, network isn't particularly good on this machine, it seems. So I'm playing video. Now let me go and stop capture. I'll do exactly the same thing I did with start. I'll just do dash stop. And I'll give it a name. Actually, before I do that, let me close IE, because you'll actually don't see this. Stopping will take a bit longer than starting. We actually do quite a bit of work. After we capture the ETL file, we also go through the system and we capture additional data that Windows itself doesn't provide us with the ETL file, so that you could take that file afterwards to another machine and analyze it there. We also collect information on things like network adapter, for instance. And I'll show you this when I open the tool. There's a sysconfig dialog box that shows you all the different data points on that system, so you would know what it is that you are dealing with. Because obviously a scenario that takes 30 seconds on a netbook might be okay, but on a 8-processor machine might be not. So notice this. The trace you have just captured may contain person identifiable information, including but not necessarily limited to paths to files accessed, paths to registry accessed, and process names. Exact information will depend on what you log. That's obvious, because we will actually tell the tool what to log. It doesn't know what to log. And please be aware of this when sharing out the trace with other people. That's just a caveat for anyone using the tool. What you capture may contain, doesn't have to, may contain something you don't want just to share out. Please let that know when you capture traces from customers. So what I have now is I have a trace of ETL that is roughly 200 megabyte in size. And I can go and open it in xperf. And what I'll do is I'll run xperf trace ETL. In fact, if you look at all the exes here, you'll notice that there is xperf view.exe. This is the real tool that's going to get used. Xperf will just forward the ETL file to it. But we thought that semantically it makes sense to both capture and analyze from a single tool name. Another thing, for security, Performance Analyzer doesn't process traces while elevated. Since I'm running admin, it's warning me that it doesn't want to process the trace. Why? Because a trace could come in from someone else, third party. They will let you analyze those traces, for instance, your customer. And even though we try to do our best not to have any buffer overflows, you never know. So we will always unelevate you when we analyze. Of course, if you run this from non-admin, you will never see this message. Now, let me also show you something else. This 200 megabyte file seems big enough, right? I'm going to go and convert it into a textual representation. So I'm going to run this xperf-i trace etl-o trace txt. And this is calling what we call a dumper. And I need to put this somewhere else. Actually, let me output this to D. Nope. Demo. There we go. Doesn't like me writing through it. So while it's doing this, and it's going to take a while, and you'll know in a second just why it's going to take a while. It's going to be a pretty big file. Let's see what xperf actually shows you. There's going to be a lot of different graphs. Anytime you open any ETL file, there's going to be a lot of different graphs. In fact, you can see them if you click on this. Not necessarily standard Windows UI, but a very useful chevron nonetheless. We call this a flyout, or the frame list. And it's going to give you the list of all the graphs in the tool. And right now, some of them are enabled, some are disabled. I can enable and disable more. Let's just stick to what's enabled by default. Let's see what's in here. So there is CPU sampling by CPU, right? This is the graph that shows you all of the CPU profile interrupts that fire every single millisecond. So there's 1,000 samples a second that Windows is doing, and showing you all of the CPUs, and we have quite a few, 8 in this case, that are doing some work. You can go and filter. This is called the legend. You can go and say filter to just CPU 7 and see what it's doing, CPU 6. There is a CPU frequency graph. You'll see this going up and down, especially on mobiles. Starting about 5 years ago, both Intel and AMD have done really significant improvements in power management of their CPUs, both in terms of P states and C states. In fact, this is the P states CPU frequency, and this is the C states, idle states. So this is where the CPU is throttling up and down in frequency, and this is where it's turning itself off and on in chunks. Disk I/O and disk utilization are graphs specific to the usage of disk. The disk I/O is a temporal histogram, so it's bucketing in this case every 5 seconds. And it's showing you reads, writes, and flushes, the only things that the disk can do, really. Both broken down in terms of low priority versus all priority and normal priority I/O. So I can, for instance, go and look at just the reads on the system, right? Or just the low priority reads, something that a super fetch, for instance, would do. And this one is for all disks, yes. There is actually, this is a good question. So is this for all disks? Yes. There is a detailed graph that you can go to if you want to look on a per disk basis. This thing. And I can actually go and select, say, this area, because I'm curious what was going on here. And this is pretty high.
So if you're tracing the disk, the load of tracing itself will show up and make that?
You would think so, but they managed to do instrumentation so low overhead that you don't really see it, yes.
Okay.
Yep. And I'll have numbers of just how low the overhead is afterwards.
Okay.
On the C-state graph, you show the depth of the C-state?
The depth of the state? With C0, C1? Yes, yes, yes. So the question is, on the C-state graph, do I actually show you? It's not on the graph. The graph is just normalized, but if you go to the summary table, you will see that this is all C1 in this case. You would see C2, C3 if it was actually sleeping, but this machine doesn't like to sleep, it seems. But I'll get to summary tables in a second. Let's go to the detail graph. So here you can actually go and choose which disk you want to look at. And this is on a per disk basis, actually per volume basis even, it seems. And you have quite a bit of information about the disk, its partitioning, its size. You can zoom in. The red lines, those are flashes. This is a legend of processes, so you can see which process is accessing. I can, for instance, just look at what IE was adding to the system. In fact, it was adding quite a bit. Most of it was from IE. I was running the IE scenario in this case. I can go zoom in. I can go look at individual IOs and see which file, which process, thread, ID, everything. And yes, like the question said, this is actually very low overhead, so it's not really impacting the system at all, almost. When you will see this impacting the system is in the server scenarios. Once you start doing tens of thousands of IOs, that's when you will notice the cost of tracing. Disk utilization is just like CPU utilization. We just see how much of the unit of time we are waiting for disk to complete some IO versus having it idle. And most of the time, it was actually idling in this particular area. We did use it almost to full extent. This is a very useful graph. In fact, this is a graph you usually start with. It's a process lifetimes graph. And it shows you every single process that was running throughout the trace, before and after, as well as those you started and stopped in between. Notice IE that I went and started, right? And then also notice this little thing. If I zoom to it, this is xperf. So xperf is not running while I'm tracing. xperf is only running when I start, right here, and when I stop, right here. Windows is the one that's tracing everything. So this is not a tool like you used to with performance analysis where it's instrumenting binaries and adding overhead. The tool is not running.
So basically, xperf sets up some hooks that cause Windows itself.
Correct. xperf is telling Windows to go and enable logging. And I'll go through the details afterwards. Another really interesting graph, especially for the application developers, window thread in focus. At any point in time, you see which window was in focus. So I was running Zoom It here. This is Task Manager. I explore. You see the PID and the TID for every single process that was in focus, or every single window, sorry, that was in focus. Again, you can filter if you want by any of those. And there is more, right? There is more graphs. In fact, you'll find out that there's probably more graphs than you will ever need. There are going to be many optional add-ons that you'll probably never use. It's a very broad tool, just like Windows Debugger, and you'll need to find what it is that is relevant to you. And chances are, you will always use CPU, and you will always use disk. Maybe not everyone will use CPU idle state, CPU frequency, or DPC usage. But the graphs that I enable by default, I bet you will use. So summary table, something I showed just previously, let me go to this again, is a data-driven approach to visualizing the data. So all the graph gives you is a first-level triage. You can see where in the trace you want to look at. Because unless you're looking at the right place in the trace, and it's going to be a very big trace usually, you don't even know where to look, right? So let's go back to the command prompt. This thing has finished. Let's see just how big that trace actually is. So we're talking 1+ gig of text. Do not open a notepad, even on this machine. Sorry? The ETL was about 200 meg. So it's roughly size of order of 10, usually, maybe 5. Usually it's 10. If you do stack, I didn't do stack decoding because I don't have symbols for this machine right now, it would be a lot more. But this is what it looks like. It's going to start with definition of events. So the first field is going to tell you what the name of the event is, and subsequent fields will tell you what the name of individual fields are going to be. And if you scroll enough, it will start seeing actual events. For instance, this is stack, and also the fields for it, right? And you'll notice that stacks are not decoded right now because I don't have symbols. This is a gig of data like this. Good luck analyzing this. And this is all that's been available to people before 2007. So the first time we released those tools was in 2007. And this is all people could work off of. Certainly, this is a much better view of the same data, right? And let me briefly talk about the summary table and what it is. Because I think this is where all the power of XPerf is. It's not the graphs. It's not the ability to capture ETL files. There are other tools that can do this. It's the summary tables. The summary table is essentially a pivot table that lets you ask various questions. That's really all it is. This gold bar separates two sets of columns. Columns you pivot on from columns that are being aggregated. So right now I'm pivoting by process, module, and then function, and I'm seeing aggregation. Let me unpivot and just look at the raw data. I've selected about 10 seconds here, right, of data. And what this translates into is, if I scroll down, about 85,000 samples. And each sample is just CPU waking up with an interrupt and saying, where am I? And recording where it's at, right? And here it's idling for quite a bit. Here it managed to hit audio DG-EXE. And we record which module, which function. Again, I don't have symbols right now, but you'll see in case studies actual function names. What's the timestamp? And the approximate weight is 1 for every single sample, right? So now if I go and aggregate, I'm going to say aggregate by process. All the idles will now be grouped under this, right? And the combined weight of them in this particular trace region is 95%, contributed by about 81,000 samples. Why is this useful? Well, I know where my CPU is going towards. So in this case, I was using IE, and I only spent 3%, which is actually really great. I was playing video, and still 3%. Let me actually select a bigger trace region, the one that corresponds to IE. So how am I going to do this? There are a couple of ways. I can go and select IE here, and then clone selection to all the other graphs. And this way, I'm looking at exactly the scenario of IE. Or I can say overlay graph, CPU sample the process. I need a lifetime graph. So process lifetimes graph. And this way, I'm going to see one graph on top of the other. And I can say that from here on to here, I was doing IE. XPerf was not running, right? We were not interfering with the system. This is real-life production scenario. I'm going to right-click on this summary table, and I'm looking at about 71 seconds worth of data, in which IE really only spent 2%. So this is great. I was interacting with an application that wasn't using much of CPU. This is really great. Try other websites, more video-intensive websites, other plugins, not Silverlight. You'll see a very different picture. You'll see other components come into play. This is antivirus. This is Microsoft antivirus, 0.25%. Again, very light overhead. Now, this machine obviously doesn't have any performance issues. I'm just capturing a trace to see what it's at. So it's really explorative analysis at this point. We don't typically recommend people do explorative analysis unless you're reading Windows internals and you just want to go and see what the system is doing. So please, whenever anyone gives you a trace, ask them to describe exactly what was happening that they're complaining about. That way you will actually be able to find out in the trace quickly enough where to look at. Otherwise, there are going to be 99% of the issues that will never be an issue for the customer, and you'll try solving the wrong things. So back to the summary table. I can also go and group by, say, module. And now I'm doing two-dimensional pivoting by process and then by module. So say for iExplorer, I can see the breakdown of where exactly I'm spending what time, right? So you can see how very quickly this becomes a generic tool. If I go to, say, disk summary table now, I can ask questions about what processes I use in disk and to what files are they writing and reading. And this is where the PII issue is coming into play, the person identifiable information. You'll see here things like your MSN contact, right? Because it's just clear text whenever you're accessing registry and things like that. All right, so that's about all I'm going to show you since we are pretty short on time. And I'll show you some live demos afterwards, so you'll get to see more of the tool. But let me briefly again iterate on what's inside the performance analyzer. Xperf, you've seen Xperf. Xperf view is the GUI, and that's really what I've been using behind the scenes. There's another tool called XBoot Manager. In fact, there's two X's, XBoot Manager and XBoot Manager Sleep. And it's an on-off transition trace capture. I'm not sure how many of you actually care about boot, shutdown, standby, resume. You should. It's actually one of the key scenarios for Windows 7, and actually was for Vista as well. But for Windows 7, we really, I think, nailed it down. The biggest problems right now are in the ecosystem. Again, a single service, a single application on startup path can add tens of seconds and completely destroy the huge improvements that Windows has made from Vista to 7. But that tool will let you capture those traces. It's not very easy, actually. It's not a matter of Xperf start-stop. The system has to be rebooted multiple times. It needs to learn, because Windows actually learns when it boots. And it needs to come to a steady state in which it's actually meaningful to analyze data. The two other tools is hardware power to TW. If you ever want to do power analysis, you can actually go and get an instrumented system, capture TDMS data, which is going to show you voltage, current, wattage on every single component in the system, and see just how much your code is affecting that component. You can measure graphics power usage, you can measure disk power usage, whatever it be. If you're working on mobile devices, that might be very interesting for you. And SIM cache gen is something you can use to generate SIM caches from PDBs. I haven't really spoken to what SIM caches are, so I'll cover that a bit later. But trust me, SIM caches are good, PDBs are big. They're not bad, they're just big. And here's a list of the basic operations that you have seen. How to capture trace, you've seen a graph, a frame list, you've seen a legend, you've seen a select, a region, and you've seen the overlay graphs. You've also seen a summary table with the gold bar that separates pivoting columns from the aggregation columns. I haven't really shown you column chooser, but it's just like the frame list. It's this little thing again called the column chooser. And in some summary tables, you will have a lot more columns than this. You'll have, in fact, so many that you will need 2 columns to represent them. Most of them will be disabled by default. Those are the more advanced summary tables. And sorting, sorting is just like an Excel. This is right now sorting by weight. You see this little triangle. I can sort by anything else, really. This is much better shown in a different summary table, but you will see this again when I do live demos. So hopefully you understand why the tool is exciting. Let me give you a bit of a background from where it comes from to help you understand that it's actually not just another tool that some guy wrote in his basement. This is the official kit. WPT is an official kit produced by Windows Organization, primarily for Windows Organization up until 2007. So for the past 10 years, really 10 years, there's probably 50 dev years that went into this tool to go and enhance it. And we're right now at version 4.0. Well, in fact, 4.6 is the one that shipped recently in Windows 7 SDK. It's a tool that is used by entire Windows Organization to produce Windows. So that's what we use to go and understand what the performance problems are and help optimize them, confirm that we have fixes that actually address those issues. It is widely supported across all 3 architectures, x86, i64, and x64. Both client and server are supported, starting from Vista and up. So I'm sure some of you have questions. Will this work on XP and 2003? No, it will not. Not because the tool will not. The tool actually run fine. The instrumentation, which is what you're really capturing, the data from the instrumentation, was not added until Windows Vista. So much of the data will just not be available in previous OSs. It is publicly available. This is true as of February 2007. We have shipped this first in 2008 SDK. There was 4.1 back there, and Windows 7 SDK now has 4.6. Do not use the old version, use the Windows 7 SDK version, because the old version is not compatible with Windows 7. You will not be able to analyze Windows 7 traces with the 2008 SDK version. Like I said, it contains other tools, not just Xperf. We will focus on Xperf in this talk. We barely have enough time to just cover basic Xperf introduction. And if you do care about GPU analysis and graphics analysis, do look into GPU View. This is the tool that is being produced and managed by the graphics team within Windows. This is, again, their bread and butter. That's what they use to develop the graphics stack. And same goes for WPF Perf tools. This is the tools that are coming from the WPF team. And this is a strategic investment. This is not something we have built and are going to just discard. We're going to continue investing in the Xperf train as long as we build Windows, because those are the tools we use to build Windows. In addition to building Windows, we've also used this across the ecosystem today. Already, I can say that about every single OEM, every single ODM has seen Xperf through FQTS, through WLK work. In fact, the reason Windows 7 is so great performance-wise is because, unlike with Vista, 2 years ahead of RTM, we've engaged with the ecosystem. You could say, learned a lesson and started working very early on to make sure that whatever solutions our partners provide are actually performing well on the bits we're going to ship. And what we've used is Xperf for this. So those are the tools you can use to both capture, post-process, and you've seen me do dump, right? Dump is a very basic way of post-processing. You go for a single event, and you just dump out ASCII for every single event. There are more complicated actions. In fact, while I'm not going to cover actions, because that's pretty advanced for this talk, if you're curious, go and do Xperf-help processing, and it's going to give you a list of the various actions that are inside the tool that you can run. One of them is going to be dumper. And when I said Xperf-I ETL-O text, really what I said is -A dumper out to text. That was just a shortcut for it, because so many people use it. But there are lots of other dumpers. So like I said, this has been in development for over 10 years. It's right now in 4th generation. And this is really product quality code. It's not a tool quality code. And I have a few reasons for me to say this. One of the reasons is that some of this code is in Inbox. It's both in Vista and Windows 7. So the internal diagnostics in Windows 7, specific to performance, leverage the same code base, some of the same code base. We have an entire dev, test, PM, UA team behind this. You'll actually see MSDN documentation online. And we use this across all of the builds that we do daily of Windows. So think about thousands of builds that Microsoft produces daily for Windows through various branches. All of those run through performance gates based on Xperf. It has really gone through petabytes of ETL files, hasn't crashed. It is enterprise grade. So the question is WPT redistributable? And can you link the MSI so you could redistribute it? And the answer is yes. You have to include the entire MSI. You could not redistribute parts of it. But as long as you deploy the entire MSI, the EULA will actually say that it is redistributable. The only way you can actually programmatically depend on top of it today is dumper. We don't have public APIs. We are working on this, so that will be in the next version, V5. So why should you use Performance Analyzer? Obviously, this is not the first performance tool you have seen, right? Quite a few of you raised hands and said, yes, I'm doing performance work. Well, this is about the only tool I know of that enables you to do holistic performance analysis. And what I mean by holistic is that you see the entire system. Most of the tools I've seen as a developer before I saw Xperf were user mode, single process, right? Or just kernel mode, sample profile, and nothing else. This tool will show you disk, CPU, network, power, graphics, right? Everything. And you can correlate everything in a single set of graphs. You can see how my CPU is working with respect to GPU, with respect to network. You can see both kernel mode and user mode code. You can see every single process, every single thread, even the idle thread. You can see everything, literally. There is nothing in the system that you will not see. And again, this is because Windows itself is using this to optimize Windows. We need to see this. It's also the only tool, I think, available that lets you capture the problem as it happens on a customer machine. You don't need instrumented binaries. You don't need lab environment. You give 2 binaries to a guy, say, run this command, and come back to an ETL file you can use. We capture things in China when send it to Redmond, or vice versa. It works everywhere, literally. And it's very low overhead. And I showed you that it's low overhead, but I can actually speak more to this later. The overhead is so low on a client machine, you will never see the impact. Some of the issues you can actually analyze with WPA, Windows Performance Analyzer, are responsiveness issues. Why is it not responding? Why am I hanging the UI? Long delays. My UI is not hanging, but it's taking a long time. What am I spending it on? High CPU usage, high disk usage, very slow on-off transitions like boot, shutdown, resume, and poor battery life. There is, of course, much, much more. This is just the basics. And I'm not going to even show you those basics. I'm going to focus on maybe 3 case studies, and that's it. And we can spend weeks doing more. Luckily, there's a lot of material online, so after this talk, you can go to MSDA and you can read the white papers. There's a lot more. And there is a forum, so you can all come to the forum, ask questions, and educate both yourself and others as you learn the tool. This is the big picture of how it all comes together. It all starts with DTW. Without DTW, which is event tracing for Windows, that really is Windows itself, that's not the tool, we could not possibly get the data. And it's just a bunch of buffers in memory to which providers log. And here are the providers. You can write your own provider. In fact, I will recommend that you do, that you instrument your own code and become an ETW provider. That way, whatever you produce, you can enable and add to the same ETL file and then visualize an XPerf. And you can correlate all the system activity against your own application's activity. You control the providers using XPerf. It's essentially an ETW trace control mechanism because you can enable, disable providers and log into 1 or more sessions. What you get back is an ETL file. That's what Windows produces, nothing to do with us. But that ETL file is not perfect yet. It is not portable. You could not move it to another machine, or you would not be able to decode on another machine. So what we do is we inject additional metadata, symbol information. We go for every single image on the system, every image of every single process that we saw in the trace, and we extract debug IDs from it, so that afterwards we could actually match it to PDBs. We also, like I said, add additional information for sysconfig purposes, something that is not logged, but we still need anyway. And then there are 2 ways to consume this. One way is XPerf view. That's what you've seen through graphs and summary tables. That's the GUI. And another one is actions. You've seen a very basic action called dumper, and I've shown you a list of other actions. And you can produce XML files, CSV files, text files. I'm afraid there is no good standard right now, so once you run an action, you'll see what kind of data it produces. Mostly it's going to be CSV. People use this a lot for Excel, so they dump data from action into a CSV file, open an Excel, and do additional analysis. So like I said, ETW is really the magic behind the curtains. Without ETW, it's all pretty much impossible because the tool is not running. And ETW is not a new component. Even though we're really introducing this to the general public, I would say Vista Windows 7 timeframe, it's been around since Win2K. Long, long before even I joined Microsoft. And what made ETW really powerful is folks at Microsoft chose to use it for performance analysis, so they started driving improvements into it. And the Win2K version of ETW wasn't nearly as robust and as low overhead as what we have today in Windows 7. In fact, if you want data points, if I'm going to be logging 10,000 events, sustained throughput, every single second, I'm only going to utilize about 2% of CPU on a pretty low-spec CPU, 2 gigahertz. So it is pretty impressive what ETW can do today. If you want more details, and in fact, I urge you to go and read more on ETW, so you instrument your own components. Go on MSDN, look up event tracing. All right, we're done for the boring stuff. Let's go and do something more interesting. Yes, question?
Is it that I no longer need to use perf1 and I can just use this only?
So the question is, should I stop using perf1 and use this instead? Perf1 is based on performance counters. This is a very different infrastructure from ETW. Very different radically. Perf1 allows people to essentially pull data, sample data, whenever they want. And they set up frequencies such as 1 second, 1 minute, depending on what kind of tracing range you have. Perf1 is not replaced by ETW. It's a complementary technology for very different type of analysis. If you want to capture hours of data, there is no way you can capture ETW. It's too verbose. It's too high frequency. So perf1 will let you do analysis like long-term memory usage, right, over weeks of time. Do I have a leak on a server? I'm going to go and sample every 15 minutes, for instance. ETW is going to let you drill down on a specific performance issue once you found it, right? And there are ways to catch performance issues with ETW. I can actually tell it to always run and then snap when the performance problem happens, and the last, say, 2 minutes will be in the trace, right? But you cannot capture hours and days. So you've seen how we capture data, right? xprof-start, and then name of a profile. The one I used was general profile. I recommend you start with it and don't play with other trace profiles for now until you get comfortable with what xprof can provide. Let's look at an actual example of something that the customer would see. And the first one I'll do on slides. Afterwards, I'll use a live demo just to show you here the mechanics. So the customer was sitting down on his machine. That was a developer running Task Manager. I'm sure all of you run some kind of a Task Manager in your tray area just to see what the CPU is doing. And every now and then, it would spike to 100%. For 2-3 seconds, it would go away. And it will happen now and then, not clearly why, right? Some people are really spooked about this, and they think, oh, I have a virus, I have a Trojan. I must understand what's going on. So without xperf, you would literally need to see with Task Manager and wait like this until the process actually comes in. There are better tools in Task Manager. There's Process Explorer from sysinternals. But even there, you have to go literally sit down and wait until the problem happens. It's not something that you can just capture and look at afterwards. So the guy ran xperf. Soon enough, he saw again the problem, snapped a trace, managed to get this into the trace. So we're seeing 0 to 18 seconds in this trace. And identified that the problem is coming from sidebar, because this is where most of the CPU usage is at. And he singled it out to sidebar.exe. So using the graph you've already seen, using the tool you've already seen, nothing new, right? He loads symbols, because he wants to understand why. And I should probably actually zoom it here as well, so you guys can see. So I'll use one of the best tools that Mark has written, especially if you present. So what you see is that sidebar, in this case, is the topmost process using 33% of CPU, right? And the obvious question is why? Why am I spending so much time? Sidebar is supposed to be this non-intrusive process on the side that's just showing me a bunch of gadgets. So again, we look at the summary tables grouping columns and aggregated columns. And what we do here is we group by or pivot by process and then stack. And we look at weights. So that's aggregation of it. And what I'm going to do is I'm going to go and expand the stack column. Now, all of you are developers, I hope, and all of you know what stack is. But you'll see a new concept here, which is a stack group. Think about all the samples. There are thousands and thousands of samples of stacks. What we do is we combine and group all of those samples from, say, sidebar exe process into a tree of all the common paths. So in this case, when I open it up, I'll see that the most common code path through all of the stacks that I have sampled for sidebar.exe is right here, right? And you'll see soon enough that there's JScript involved. In fact, starting about 11%, we start using JScript a lot. And you see what that JScript actually does. Invoke exe, invoke def, execute call, run, dispid. I mean, think about a very long line of guys that's just telling the other guy, go do some job. And that's exactly what's happening here. We have asked JScript to do something, and it's just redirecting until we get to this place, which is msfeeds.dll. Now, you may figure out by the name, this is RSS feeds. This is the DLL, the native DLL. That's really only eating about 3% of CPU here. That's just fetching every now and then your news. But the overhead of actually calling to it, getting to it, has been chosen pretty poorly. And the overhead is about 10 times more expensive than the actual work involved. So that's why you see that high CPU usage. The recommendation here would be go use something lighter weight, maybe not JScript. OK, case studies. We have about 15 minutes left. I'm going to try and complete all the case studies. If I don't, every one of those case studies is in the slide deck. and I have put in build slides so you can like, literally go through the same demos I'm going to show you today. The very first one is from a guy that came back from vacation after being off for 2 weeks. And he logs into his machine, he downloads a whole bunch of messages. He sees, in fact, about 1,000 messages. He decides, I'm going to mark those 875 whatever messages as read. I'm not going to read them. It's going to take me a month to read them. If they really care, they'll email me again, right? That's what I'm going to do when I come back from PDC, actually. Of course, they will all email me again. That's the problem. So let's see. The file is about 96 meg. It's smaller than the previous one. In fact, whenever you capture in buffer, it's using 5% of your system memory. So the more memory you have, this machine has 8 gig, which is why you got this big of a trace. The more memory you have, the more data you'll get. I think this guy must have had maybe 2 gigs. And you can actually find this out. I can show you how. But let me go and start this. There's this thing called SIM cache. It's just a bunch of files. Some of them very small, others slightly bigger. A PDB for the same binary will be about 10 times the size. So when you think that 2 megs is big, that WCP.pdb was about 20 meg. SIM cache is really a stripped down version of the PDB that has only the information needed by xperf. It's literally just the names of the function, nothing else. We don't care about parameter names, variables, types, nothing else. So that's all we capture. And the reason we do it is because it is much faster to load a SIM cache in a PDB, and archiving is much easier. We actually have archives of SIM caches, just like those traces, back from Vista days, which we can carry on for years and years. With PDBs, it's just not possible. So I'm going to go and say NT-SIM cache. And you can do this from the GUI. So next time maybe I'll do it from the GUI. This time I'll do it from command line, just to show you the different ways. So I'll say that NT-SIM cache path is this particular path. And I also need to do one additional thing that you will never have to do. Those traces are pretty old. And the version of the SIM caches is pretty old. So I need to actually tell the tool that, yes, you can use the old version of the SIM caches. And I'm just going to start it. I can appreciate just how fast xperf really is whenever it's loading traces, because it's going through millions and millions of data points. So what do I see here? I see CPU sampling by CPU. This is a graph that's showing me how CPU was used, right? And it is not bottlenecked, so it's not a CPU problem, right? It's not a CPU bottleneck problem, I mean. But let me actually go and see that I'm looking at the right data, because frequently the customer will give you a trace, and they will capture the wrong data. So don't even bother looking at the data unless you understand that it is the right data. Mark my words, you'll do this enough times. So here's Outlook. It is a top process. We are using about 5% of CPU, maybe about 6. And if I expand, so module is not going to do me any good. But if I, in fact, use stacks instead of module, and look at what Outlook was running, and I expand down the most used path, which is not much, it's only like 2% here, I do see that it is marking messages as read, right? So I am looking at the right code. For duration of 113 seconds, Outlook was spending about 2, 3, 4% of the time marking messages read. And the question is, what the hell? Why? Why is it sitting and sleeping like this? Well, chances are it's waiting for something. Let's go down and look at disk. Remember this graph? Disk utilization, right? It was pretty low utilization on my trace because I had no performance issue. Well, in this case, the disk is absolutely dying from requests. In fact, requests are just piling up and up and up and up, and I cannot catch up. If I look at the legend, it's really only disk 0. And if I look at all, it will be pretty much a straight line. The only reason it's not a straight line is that we're not sampling fast enough. It would be a straight line. The disk is getting really more IOs that it can handle. So a good rule of thumb number for today's disks, if you see more than 110 IOs per second, you're in trouble. It's about 80 to 120 for rotational disks. Now let me go back and enable this, and let's see what it's doing. So I can go to the summary table and look at the top processes. So the very first one, remember this trace actually came from Vista RTM. So this no longer exists as a problem. But search indexer, our friend search, is using 39 seconds, almost 40 seconds of disk out of those 112. And then system is the next heavy user. It's using about 30 seconds. Then comes some service, trusted installer, and then finally Outlook. And Outlook is only really getting about 7 seconds of disk out of 112. So first level triage, people are fighting over a single shared resource, which is disk. And Outlook is not really winning. In fact, it's losing. And that's why the user is really not enjoying his experience. I mean, 2 minutes, I would kill Outlook at that point. The guy was really patient, I think. You can also see what path names are being accessed. So for search indexer, you can see that this is the top file. For system, you can see this is the top file, right? Actually, interestingly enough, look at Outlook. You can see read counts and write counts here. So Outlook has done about 5,500 writes, but only 8 reads. That doesn't sound right. I mean, Outlook is doing a lot of work. How come it's only doing 8 reads? There's this really great feature in Windows called superfetch, prefetching. So Windows knows ahead of time what the application will want. It's got psychic powers. No, really. But here's an action, superfetch working. It is reading Outlook OST. This is system. And all of that I/O is going to be really benefiting Outlook when it asks for the data. I can group by path name first, and this will show me the top files being used. And you'll see that the very heaviest file being used is Windows EDB. This is JET database for search indexer. That's where search is actually storing all of its indices. And we'll spend about 38 seconds on it. Outlook OST is the second biggest hitter. We actually have spent a lot of time on Outlook reading. And that's why we haven't seen this in Outlook. It's 28 seconds reading, right? We've been doing some paging. That's another JET database for edge remove programs, trusted installer. Now, second level triage. So we know we're fighting, but why are we fighting? Obviously, Outlook did not ship a product like this, right? So the reason they did, and I can assure you they have tested against search indexer, they have tested trusted installer. This is Vista RTM bits. And the reason they missed this is because a guy came back from vacation after 2 weeks, right? No one in the lab tests after 2 weeks. No one sits for 2 weeks on a machine and then says, okay, let's see what the system is doing now. Because you have so many other things to worry about. But in this case, you log in, the machine has been off for 2 weeks. It's downloading emails. Search indexer thinks, oh, I must go and index all of this. Because, my God, he's going to type something. I need to be able to provide an answer right now, right? And then trusted installer, Windows Update says, security updates. I got to check out what's on the system, because maybe I'm out of date. 2 weeks have gone by. So those two components take over the machine, essentially. And while the user said, I want to do a specific task, mark messages as read, he's not given a chance. The solution was actually very simple. Both of those components in Vista SP1 and on use task scheduling. So they get scheduled as idle tasks. And that's what we recommend people do. Unless you believe that whatever you're running should execute right now because the customer is expecting it, do not run at foreground. Schedule idle task. Windows will know when to run you. It will be pretty soon, trust me. We don't just delay you until end of time. So that's probably the longest demo I had. But again, you can go through the case study yourself. I'm going to very briefly skip through this. It has all of the steps. So feel free to capture your own trace and play with this. This is the message you need to remember. Throughput can be cut by 90%. If you're using a rotational disk, you start seeking. Anytime you start seeking heavily, you will cut your throughput by up to an order of magnitude. So if it was 10 seconds, it will be 100 seconds. Don't let the disk seek, or put SSD on it if you really have to seek. The summary is that multiple components working well in isolation, and each of them works very well in isolation. You put them together, it's going to drastically impact performance if they start fighting over resources. And do use idle tasks for this kind of stuff. So in this case, user complained that the system was very slow. This actually is a very simple demo. I don't need sync caches. The user has complained that everything is very slow. Boot, opening Internet Explorer, start menu. In this case, I recommend check the system. Maybe the system is bad. Don't spend your time understanding what did I do wrong in my code that the user is complaining. Chances are the system is bad. And fair enough, CPU is not bound. We have plenty of cycles. In fact, if I go and select, I'll see that I'm only using about half of it. System was non-idling 60% of the time. So it's not CPU. Let's look at disk. Because if it's not CPU, usually it's going to be disk. Well, if it's not, then it's network, but we're not going to cover network. And yeah, the disk is actually pretty heavily used in this area. In fact, I can select the whole thing and look at summary table. Now, you will not actually see here any specific process, and I don't need path name. You will not see here any specific process that is contributing a lot of time. There will be system. Yeah, there is system. And you open up and you right away see the answer. 954 milliseconds, or pretty much a second, was spent on a single I/O, which was 32K in size. Another one, another one, another one. Really small I/Os, really long time, right? So you can say from this right away the disk is bad. And you will not see here any specific process that is contributing to all of this. In fact, I'm sure you guys know what paging is. If you go and look at the pagefile.sys, it's got to be somewhere at the top of this. And remember that paging is asynchronous I/O, so if I'm paging, I'm blocked. Nothing can run. You'll see that 15 seconds total I spent out of 266 paging. And every single time I page, for that second, for that 0.7 seconds, nothing runs in the system. I'm bringing stuff from memory. So this was a simple one, right? Again, you would not be able to use any other tool to diagnose this. That's a good view. Do ungrouping, don't pivot by anything, and sort by service time. You'll see that it starts at about 1 second and goes down. Not all IOs will be that bad. Some IOs have been cached, so you'll actually see them running in milliseconds, if not microseconds. Third study. We're really very short on time at this point, so I apologize. But so if you want, I can skip and just go to the conclusion. You can do this yourself since it's in build slides. But I can actually go through this if you have a few more cycles to spare. Continue? Okay. So the same guy that came back and waited for 2 minutes for Outlook came back from vacation, right? He brought some photos with him. So he says, okay, Outlook is not working. I'm going to go and look at some photos. He takes his SD card, puts it into his computer, opens up Explorer, and starts looking at photos. He also happens to play music. Most of us do. Music starts glitching really heavily. Now, some would say this is not a performance issue. This is a reliability issue, right? Well, in fact, it is a performance issue, and you'll see why in a second. So I'm going to do again the same thing, but this time I'm going to configure this from the UI. Those are actually real traces from real people. This is alias of a guy. This is the date when it was captured, right, the time. So this is all real data from customers. So trace, configure symbol paths. I can go and tell it to use. If you don't have SYN caches, you specify anti-symbol path, just like in WinDBG. It will generate SYN caches for you. That's how you get SYN caches. I'm going to load symbols. And I'll see, first of all, CPU is not really pegged. If I go to summary table, 78% of the time I'm using the CPU, but the rest is really idling. And there's another way to see this. Idle process, 21%. Right? So I'm not bottlenecked on CPU. Why is my music glitching if I have some CPU cycles left? It's not even the top process. I don't see Windows Media Player, any kind of player. There's X audio here. And it's really, there's audio DG here. 1.8%, really? Not that much. So what's going on? Disk? Nope. Not bottleneck on disk either. Plenty of disk cycles. So there's a concept that I'm going to introduce to you that most of you probably don't know about if you are application developers, called DPC, which is a deferred procedure call. This is something that Windows uses to handle interrupts. So anytime a device needs to talk to the OS, it raises an interrupt, which must be processed very, very quickly. Otherwise, your machine hangs, because nothing else can run. And what we do is we schedule a DPC, a deferred procedure call. It is deferred until later time. DPC is much lower priority than interrupts, so that we could handle all the interrupts. And they come in at very spurious rates. But DPC is still higher than any user thread that you will ever run. The highest priority you can think of, DPC will still preempt. In fact, DPC is running at the same level as the dispatcher, the scheduler. So anytime I'm at dispatch level, the schedule is not scheduling anything. Drivers running a DPC literally block all other user mode activity, right? So this is likely a driver that is running a DPC for far too long. In fact, we're using what? About 50%? Yes, exactly. Yes. But for everyone else in the room, let me go through the demo. Yes. So the very top driver is sdbus.sys. And we have spent about 14.4 seconds in that driver doing DPCs. To make a comparison, the next one is anti-kernel itself. If you look at the number of DPCs, it is a comparable number. And yet it spent only 223 milliseconds, so several orders of magnitude less. This is, I would say, unacceptable for DPC usage. And I think so would every single other device driver developer, if they actually saw this. Problem is, it's really hard to capture. Without expert, you don't even see this, right? No other profiler will show you this. So let's see what actually it's doing, because you already have the triage. At this point, you can say, yes, this is a problem from sdbus.sys. It's using too much DPC, done. But if you want to be actionable and know how to fix it, you need to do an extra step. And that extra step is going to the CPU sampling summary table. And looking by process will not help you at all, because DPCs fire at random processes, whatever happens to be. Interrupt fires, DPC runs next. Whatever process was running, that's where DPC is going to happen. But if I group by stack, so I'm going to remove process, I just group by stack, there is a special function in Windows called ki retire DPC list. DPCs are just a bunch of objects in a list, right? Linked list. And Windows fetches DPC one at a time and processes it. And processing means calling the right driver to go and process it. So if you go and expand this, what you will see is a whole list of different drivers that are all processing DPCs on the system. There is network, there is graphics, SDBus, ATA-port, keyboard, ACPI, right? All the different drivers processing DPCs. The only one that is misbehaving is this guy. 23.8% are spent processing SDBus DPCs. Now, again, anytime I'm in this code, no one else is able to run. And what am I doing? Fair enough, it's PIO, it's not DMA. I'm reading one ULong at a time, and then I'm writing it. So I'm using this really expensive brain called CPU to read, write, versus telling a DMA controller, go and move data into memory. And that's really what's causing it. If you go back to this disk graph, you can actually go and see. People ask whether I can see individual disks. Yes, you can. You can see in this layer that it's 118 JPEG. And then the next one is going to be 117 JPEG, right? So you can see individual files. You know when they get accessed. From that on, you can actually go back to your code and see the time ranges. A real shocker is that at Vista RTM time, 50% of laptops have this problem. And people didn't know how to choose between them, because how do you actually know whether you have a DMA control or not? Two identical machines coming from identical OEM, one would have DMA controller, one would not. It would be $100 more expensive. People would get the cheaper one. There is no way to tell. So I've shown you three types of problems. I've shown you a disk software problem, disk hardware problem, and a CPU device problem, right? You could say CPU hardware problem. There are, of course, many more, but those are the typical ones you will see. Again, feel free to go through the slides and repeat the same exercise. It does take several iterations to get this. But to conclude, anytime you think about performance, those are the 3 points to focus on. And I'm going to show you a slide deck on all the resources, but before that, go download WPT. Windows 7 SDK is where it's at. You will need to choose Win32 development tools to get it. You don't need to download the whole thing. In fact, I would advise just downloading the development tools if you want to do analysis with this. Capture traces across key scenarios you care about, and then start evaluating. Look at those traces, see where your bottlenecks are. Do invest into your own ETW instrumentation, add it to your own component. You will be able to see this in Expert then. And visit a performance analysis dev center. If you go online, we actually have a whole site for you. Where you get the library, that's MSDN documentation. Go through this. And you also have the community page where there are quite a bunch of blogs from various teams at Microsoft on performance, as well as a performance forum. This is where you go to ask questions and hopefully help some others learn the tool as you learn. So we're hoping to build a community in this forum. And here's a list of resources, the Dev Center and the MSDN documentation. Do get Windows Internals book. It's really a great book. I don't expect you guys to read it. It's about this thick at this point. I mean, it's growing an inch every single release. But it's a great reference material. Most of this you will not find anywhere else. And please provide feedback. Someone is actually monitoring all of this, and they will provide us statistics afterwards. Thank you. If you have questions, I'll be at the side. So I'll let another guy come in.